Hello, everyone. My name is Josuet. I'm the Deputy Technical Manager of the Service Robots Department, and today I'm going to give you a short presentation about the autonomous mobile robots that we have developed in our department. So my presentation is going to consist of two parts. First, I'm going to give you a short presentation of the intelligent AMR solutions that we have developed. And then in the second part, I'm going to show you some interesting applications where we combine robotics with arts. In our department, we have been developing autonomous mobile robots for quite some time, but we also have developed other type of robotic systems. For example, we develop a human-like robotic hand, and regarding the autonomous mobile robots, we have developed some mobile-based robots, and in this case, this mobile-based robot can carry 100 kilograms, but we have developed platforms for 250 kilograms, and we are hoping to develop soon platforms for up to 2 tons. And we also develop mobile armed robotic systems, like, for example, this robot here called Mars Light. Now, in our intelligent AMR solutions, we need to integrate mobility, navigation, perception, manipulation in the case of mobile armed robots, and also human-machine interfaces to use these robots. And using all this integration, we can develop solutions for the industry. For example, the mobile arm robot here that we can use for pick-and-place applications and other applications that requires the robot arm. We also have developed some applications for the autonomous forklift. For example, in this case, we developed a technology to perform the pick-and-place of a pallet. And we also have done some outdoors mobile robots where we use a robot to monitor an outdoors area for some companies. And in the case of service, we have also been developing technologies to be used in convenience store, hospital disinfection, and lobby cleaning. Now, for the case of the industrial applications, I'm going to give you the 2 short study cases. And the first one is the pick and place in a manufacturing cell. And as you can see in this video, this holonomic mobile manipulator is picking a workpiece from this manufacturing cell, and then it will place it in other locations around this manufacturing cell. This was done to mimic a real manufacturing cell where we have multiple processes that these workpieces have to go through, and this mobile manipulator will be in charge of moving around these workpieces. We also use the same mobile manipulator to perform other specific tasks. For example, here we have the LCD carrier polishing, where we use the mobile manipulator to approach this LCD carrier, and then we perform the polishing in 4 steps. And as you can see in this video, we are polishing the first quarter of this LCD carrier, and then the robot will move to the next, to the 3 other locations where we will perform the polishing task. For these industrial applications, we developed the following technologies. First, we develop a task manager and a task executor. The task manager will take the task one by one, and it will use the task executor to execute this task. And combining these technologies, we can do quick reprogramming of the robot. For example, we can change the arm trajectories, the mobile-based goal, docking operations, and other tasks. And this task definition uses a simple and intuitive XML format. So this is really easy to reprogram these robots using this task manager and task executor. And this task executor can also use relative reference frames. For example, in the 2 videos that I show you, we use April tags to reference how the movements are going to be done. And these 2 technologies are also easily adaptable to a dispatching system or a manufacturing and execution system using a task server, which leverages the task manager. Now, in the case of the service applications, we have the lobby cleaning, as you can see in the top left. This is an Ackerman type robot, and we use this cleaning robot. We adapt our technology to this existing cleaning robot to perform lobby cleaning. And in this case, you can see the robot is performing this cleaning trajectory that we computed based on the cleaning area that the user wants to do. We also have the hospital disinfection, which uses a similar technology where we can select the areas that we want the robot to clean, and then we can also select the areas that the robot should not go to. And this was already applied in the National Taiwan University Hospital here in Taiwan. The technologies that we developed for these two service applications was a multi-area, multi-block cleaning path generation, which this means that if you have a big map and you want to clean multiple areas, you can select these multiple areas one by one, and also select some blocks that you want this robot to go to. And then the robot will find the optimal path to move between these two areas. And we can also select the forbidden areas, which are the areas that we don't want the robot to go, maybe because we're doing some maintenance there or for any other reason. And we also develop an intuitive operation, which is an Android-based HMI, as you saw in the lobby cleaning case, where we have this, the screen to select the map that we want to use for this cleaning, or to select the task schedule or other tasks. And this selection of the allowed and forbidden areas can also be done through this HMI. And we can also generate the task schedule for all the tasks using the HMI. Now, we also have been doing some research to execute complex trajectories with mobile manipulators. And as you can see here in the top left, the robot is moving around this Lissajous path, and it's continuously tracking this trajectory while it moves. You can also see on this second example that the robot is following a sinusoidal path. Now, this type of trajectories can be used for certain applications where you actually want the mobile base and the robot arm to move continuously. A simple example is if you want to open a door, you might need to do this. You can do this one step by step, first moving the platform and then moving the arm. But a more optimal way to do it is by coordinating the movement of both the arm and the platform to open the door. And the technologies that we develop in this case is the coordination of the robot arm, and in this case was a non-holonomic mobile base, but we can adapt for holonomic and non-holonomic. Just the non-holonomic case is more challenging, so that's why we work on it. We also had to do the redundancy resolution to execute these complex trajectories, because this is a 10 degrees robot, 10 degree of freedom robot arm. And because this is a highly redundant robot, we also need to consider the singularity avoidance to allow the robot to perform this task. We also included a self-collision and joint limit avoidance as constraints to execute all these paths. So in both videos, what you saw was the robot executing this task and continuously avoid the singularity, and also continuously avoiding self-collisions and joint limits. Now, in the second part, as I say, we're going to show you some examples of how we combine robotics with arts. And in the first case study, we have the free-person project by the artist Taoya Lueng. And this project was presented in the Patch Lab Digital Art Festival last year in Krakow, Poland. And in this case, what the artist requested from us is he wanted to use a VR headset that you can see on the top left video. And the headset is at the beginning showing a video that is the idea of this artist to show around the area where he's trapped right now, where he feels he's trapped because he can only see around. And then after this video finishes, we will see that the mobile manipulator on the top and the bottom left will start moving and tracking the movements of the headset. So what the artist requested is, can we follow the movements of the headset around this area? So he will walk around this area, as you will see in a couple of seconds. So as you will see here, once the video finishes on the top right corner, the mobile arm robot will start moving. And what you see right now on the top right is the stream of the camera mounted on the end effector of the robot arm. So right now, as the user is, in this case is the artist testing our project, is moving around this area, the mobile arm robot will follow his movements. So it will follow the movements of the head as well as his location around this area. And as you can see, on the stream, we're constantly streaming all the movements so that the user feels like it's actually in Taiwan. And this was recorded in a theater in Taipei, while, as I say, the user is in Poland, in another country. Now, for this specific case, we needed to develop an arm target follower. As you can see in this video, the arm is following the movements of the headset as the user moves around. And we also needed to develop a mobile-based target follower. And in this case, the mobile base needs to follow a target, and the arrow here is pointing to the direction that we have our target right now. And while it does so, we also have to consider there might be some obstacles around the environment, so it needs to avoid moving to those areas. Now, the technologies that we developed for this project was a remote control for the mobile arm robot. And as I told you, this is a remote control from a different country to Taiwan. And then we developed a smooth Cartesian velocity control for the 6 degrees of freedom robot arm, as you saw here with the movements of the arm. And this target follower also need to consider the constraints like joint limits and the workspace limitations. And for the mobile-based target follower, we included the collision detection, as I just mentioned. And all the execution that we performed was using the MQTT protocol. So this is how we receive the task from the headset to tell us where the mobile manipulator should go. Now, the second study case, we have this artist ask us to perform the movement of a mobile platform in this circular trajectory that you're seeing in this video. In this case, the robot must just move around this circular trajectory constantly while a performing is moving around it. And the challenges in this project were that first, that the lighting conditions change a lot. So we have really dark areas when the performing is moving around, and we also have really a lot of light in some areas. And this, as you can see here, the mobile base is already moving around this circle. And the problem was that because there's going to be, the audience is going to be seated around the performance area, there is no way to acquire features to actually localize the robot inside this circle. So the challenge was how we can actually develop some localization algorithm for the mobile platform so that it can move around accurately inside the circle. And as you can see here, the performing as it is moving around the circle, and we're showing some video through this transparent screen, the robot will keep moving around the circles with high precision. Now, for this specific case, we develop an indoor localization system that is robust to illumination changes. And we also develop a precise trajectory tracker for this mobile base. This is the end of my presentation. Thank you.
Thanks, Josuet, for such an informative presentation. We have also received beforehand some questions concerning your topic. So the first one is, how do your robots communicate with the dispatching system, or MES?
Thanks for the question. So as I mentioned in my presentation, the robot has what we call a task server, and this task server can be easily adapted to a different format that is used by the dispatch system or the MES system. So we can actually just write a couple of lines just to convert the format from the MES or the dispatch system to a format that actually our task server can understand, and then in this way we can execute the tasks.
Okay, thank you. Another question is, what kind of data and how did you send this data over the internet to the robot to follow the user's movement in the free person project? And also, can you use the same data and follower algorithms with other robots?
So for this project, because we were capturing the data from the headset, what we did was trying to capture the position and orientation of the headset after we perform a simple calibration. This calibration was done when the user wear the headset for the first time. We will save this data to use it as a reference for the rest of the performance. And then we will take this data and use the MQTT protocol, as I say in my presentation. And when the robot receives this data, it will filter it out so that we actually have a smooth movement and the user does not feel like weird movements because of the vibrations. And our algorithms, both follower algorithms, were developed to be used with any other robot. So yeah, we can use the same data or other data and still use these follower algorithms for other applications.
Okay, thank you. Another question is, what type of indoor localization technology did you use that is robust to the large illumination changes?
So like I said, for this project, the main issue that we had is we could not use a LiDAR technology to do the localization. Because the performance was done in a theater, we needed to find other ways to create this localization system. So what we did was install a couple of LED lights on top of the the screen that was on top of the robot, and they form a special pattern. And by using 2 cameras mounted on the ceiling of the theater, and using some estimation algorithms that detect this specific pattern, and we also calibrated the cameras to actually just detect this specific infrared light, we will try to estimate the position and orientation of the robot inside the performance area. And then using this information, we could perform the trajectory that we show in the video.
Okay, thank you. Another question is directed to a different field, to smart farming. What is your perspective of autonomous robots in this field?
So there has been a lot of development of autonomous robots in the smart farming. We are also currently working in one of these projects. And I think the main problem that we are facing is how to cost down this type of systems, because especially for the localization equipment that we need, and because we're going to use it outdoors, I believe that we need to find ways to cost down this kind of equipment, or try to find innovative ways to perform the localization so that the farmers feel more motivated to use this type of robots in their farms. Because while the prices are a little bit expensive, I think it will be really complicated to have them use these robots.
Okay. Thank you, Josué. I think that's all the questions we have for today. And so we look forward to the potential collaborations we will have with AMR technology following today's exchange. So thank you, Josué.